tonight's presentation, Borescope Meets AI. Our presenter, Mike Bush. Mike is president of Savvy Aviation Incorporated, an author for numerous aviation publications, a CFI, a A&P mechanic with IA privilege, Aviation Maintenance Tech of the Year with the FAA in 2008, a member of EAA. Mike, thank you very much for being with us tonight and sharing your information. I'm going to turn control of the presentation over to you.
Okay, good evening, everybody. Good evening, Tim. Looks like my video is on the screen, so we'll proceed. We've got so much cool stuff going on at Savvy Aviation right now. I'm almost finished with a brand new IA renewal training course for A&P mechanics and IAs who are looking to renew their IA that briefs them on state-of-the-art stuff. I've already talked to you in previous webinars about this Gadfly project that we're doing, this AI that looks at engine monitor data and detects anomalies. We've got another cool AI project that we're tentatively calling Squawk AI, which is a large language model that we're training on every piece of information about general aviation maintenance we can find, including the 180 webinars that I've done, all of the articles that I've written for Sport Aviation, AOPA Pilot, the 4 books I've written, and just a ton of stuff, and trying to develop a large language model that will be able to be an assistant for troubleshooting aircraft problems. Tonight, I just wanted to talk to you about another project that we have started recently. It's kind of been interesting. Doing this AI stuff is really a lot of fun. Let's see, where shall I start? But about 21 months ago, I guess it was, we launched a Borescope initiative, and I did a webinar about that, and actually I've done 2 webinars about it. But we felt that enough attention was not being given to using the Borescope as the primary means of determining cylinder condition. And it's just an infinitely better tool than the old compression test. And so we launched a Borescope initiative with a testing protocol and a checklist and a video to train mechanics how to do it and stuff. And that was launched on January 1st, 2024. One of our ulterior motives in doing all of this was to collect a large repository of Borescope images of general aviation aircraft engine cylinders, so that eventually we would be able to train an AI to be able to look at Borescope images and determine whether they were normal or abnormal. Right now, of course, we're doing that with our team of human analysts, but it just seemed like it would be really cool to be able to do that with an AI that could look at the images. It's not an easy problem, but it sounded like a really fun challenge. So at that time when we started this, I kind of figured, when we got to the point where we had something on the order of maybe 500,000 Borescope images, we would be in a good position to train a really good AI to look at these things. We're not quite at 500,000 yet, but in the 21 months since we launched this, we have now amassed 170,000 Borescope images uploaded in the 640 days since we launched this on January 1st, 2024, which I'm pretty impressed with that number. I think the adoption of this whole Borescope initiative has been very gratifying. we're getting on the average more than 250 new images uploaded every day, almost 2,000 new images a week. So in a couple of years, we'll probably will be at that 500,000 figure, but I just wanted to let you know where we are right now. It's a little bit early in terms of doing AI work with this stuff, but of course we couldn't stand to not give it a try. So we've been working on this. So of that 170,000 images, or 171,000 that have been uploaded to the repository, our team of analysts, about 10 analysts so we have on staff. We actually just hired another 4, but it's been mostly about 10 analysts, have reviewed 74% of those images. About 125,000 images have been looked at by our human analysts and annotated as to whether they look normal or abnormal, and if they were abnormal, what was wrong with them. And in particular, we always focus on exhaust valves because exhaust valve problems are the #1 reason that cylinders lose compression and wind up being removed for repair and stuff, which we don't like to see happen. But so our human analysts have analyzed a little over 13,000 exhaust valve images in the last 21 months. Those 13,178 exhaust valve images came from 2,781 different engines. So if you do the division, you'll find that it averaged roughly 5 exhaust valves per engine, because some of them were 6s and some of them were 4s. So that seems like a pretty rational number. And so what happens is typically the aircraft owners, sometimes they're mechanics, but mostly the aircraft owners upload these images to our repository. Then they tag the images, which means they mark each image as what cylinder it came from and which of the 11 different views in the inspection protocol that image is. And then once they've uploaded it, if they want us to analyze it, some owners analyze them themselves, but about 3/4 of them will request an analyst, our team of analysts, to take a look at their image set that they just uploaded from the inspection. So that opens a ticket. It gets assigned to an analyst. The analyst reviews the images, and he labels each image as to the condition that he assesses, whether it's normal or abnormal, and if it's abnormal, what the abnormality is. And depending on what view it is, there's various abnormalities that he can tag. And then finally, after all of the images have been reviewed and analyzed, the analyst generates a report with pictures and comments and stuff, and it winds up being a PDF file goes back to the aircraft owner that he can read, share with his mechanic, add to his maintenance records, whatever. So in the case of exhaust valves, the analysts will either label the valve as normal, heat distressed, which is burned, or cracked or chipped, eroded, or there's an undetermined category, which means I couldn't make sense of this image. It was out of focus or poorly lit or something. And if it's a heat distressed valve, a burned valve, then the analyst makes an assessment of whether it's an early stage burn valve, mid stage, or late stage. And so here's some examples of exhaust valves and how they were tagged. One in the upper left is normal, and there's a bunch of early stage valves, a bunch of mid stage valves, and a couple of late stage valves that look like they're very close to failure. Actually, the one on the upper right was actually removed from the cylinder because it was so close to failure. You can actually see a couple of fingers holding the valve stem out of focus in the background. But so these are the kind of images that they look at and the assessments that they make. And so we were able to derive some interesting statistics from all of this stuff. From the total of 13,000 and change exhaust valves that we have looked at, about 8% of them were heat distressed, were burned, and the rest of them were normal. So 92% of them were normal. So burn valves are a moderately rare event, although with an 8% chance that a valve will be burned and having 4 or 6 cylinders in the engine, the probability that you have at least one burned exhaust valve is actually surprisingly high. And if we look at the breakdown of the heat distress valves, about 87% of them were early in the early stage. They were caught early, which is one of the beauties of doing borescope inspections. It catches these problems way earlier than if you just relied on the compression test. And the remaining 13% were in a more advanced stage of burning. And the importance of this is that that means that 87% of the burned valves were excellent candidates for being lapped in place and not having to remove the cylinder. And only 13% were in a more advanced stage where cylinder removal might be necessary to replace the valve. And actually, some advanced things, valves actually can be saved by lapping, but the early stage ones, literally, we've had literally 100% success ratio in solving those problems using the lapping procedure that I did a webinar on recently, and we're big fans of doing these minimally invasive repairs that don't involve pulling cylinders off the engine. So, our motivation doing this AI project, besides the fact that it was just a fun challenge, was that, with all of these images coming in, it takes a lot of manpower and trained, expert manpower to review these valves. And our analytical team has pretty limited bandwidth with, like, as I said, we were staffed at 10 analysts. We've now expanded it to 14, but still there's an awful lot of stuff. And these are the same analysts, by the way, that look at the engine monitor data that's streaming in at a huge rate. And most of their time is spent looking at engine monitor data, and a small amount of their time is spent looking at borescope images. But the hope was that the AI, at least to begin with, could just flag valves that seemed like they needed human attention, and ultimately would hopefully take over a lot of the analysis that the humans are presently doing. So this initial project that we're working on and that I'm describing to you, we decided to make it very simple and have a very limited goal of creating an AI classifier that would look at an image of an exhaust valve and determine whether it was normal or distressed. At this point, at this stage, we're not trying to get it to grade the level of distress as early or mid or late stage. That would be probably the next step. But to begin with, we decided we were just going to develop a binary classifier that would look at an exhaust valve image and try to determine whether it was normal or not normal. So to do this, we decided to use an AI model from a company called Landing AI. It's called Landing Lens. It's a machine learning model. It's commercially available that you can train on images. It's specifically designed to do that. And it's the sort of thing that you can train on pictures of faces and say, I want you to learn how to distinguish male faces from female faces, that sort of thing. But we decided we wanted to use this model and train it on exhaust valves. This thing is this company, Landing AI, is the brainchild of one of the really amazing thought leaders in the whole AI industry, a guy named Andrew Ng, who was behind Google Brain, behind Baidu AI in China. He's a professor at Stanford, and he teaches a course in machine learning, and he's just like one of the grand old men of AI. He's not that old, but AI isn't all that old either. But this Landing Lens model was the brainchild of his company. So basically, the idea is that we would take a bunch of training data that our analysts had looked at and labeled as being normal or distressed, and if distressed, what level of distress. And we would use that to train this Landing Lens model. And after it was trained, we would be able to feed it images whose condition were unknown, and have it try to make an assessment of the condition of those images. And what comes out of the model is a binary thing that says either it's normal or distressed, and then a confidence value that says here's how sure I am that I'm right. And if a valve is in late stage distress, it's pretty easy to determine that. If it's in early stage, it can be a lot more subtle and a lot harder to determine. And so the classifier makes its best assessment as to whether the valve is normal or not, and also gives a confidence score of how confident it is in its finding. So when we first started to try to train this model, we had some problems because the images that we got, the Borescope images, were highly varied in terms of how the camera was positioned and what part of the frame the valve occupied and so on. So we wound up doing a two-stage model. The first model was just designed to find the valve and draw a rectangle around it and crop the image so that the valve images would be in kind of a standard square form factor, with the valve occupying the entire frame, instead of just being an object somewhere in a big landscape. And then once the first model cropped the image properly, then it would be passed to the second model, and the second model is the one that would look at the image and try to come up with a prediction as to whether it was normal or distressed, and a confidence value as to how sure it was. And here you can see the top valve is clearly normal, and it said it was normal with a 99% confidence. The second valve is pretty clearly distressed, and it said it was distressed with a 98% confidence value. And the bottom one is early stage distress, and it's pretty subtle, and the classifiers decided it was distressed, but said it was only 68% sure that it was right. So it gives you an idea of kind of how this classifier works. Now, as I mentioned, this is very early in the game. We don't have as much data to train as we would like. These burned exhaust valves are fairly rare, and late stage ones are extremely rare, which is why you really need hundreds of thousands of images to really train something like this right. But we took a first crack at this when we had basically 13,000 exhaust valve images to work with. About 12,000 of them were normal. Roughly 900 of them were labeled by our human analysts as being distressed. Only a relative handful, a dozen or two, were late stage distressed. So this is a very limited data set for training a model, and so we had kind of modest expectations. And in fact, as you'll see, this thing actually turned out to perform better than we would have expected at this very early stage. So we wound up putting together a training data set, or a data set of about 1,800 labeled images. And they were selected to have as many abnormal valves in the set as we could, because they're pretty rare. But something like half and half normal and abnormal valves to train with. We took this 1,800 images and divided them into three groups. 70% were used to train the model, 10% were used to tune the model, and then the final 10% were used to test and the model and see how well it performed. This is what's called a supervised model, where the training data is labeled by humans. Interestingly enough, of course, this whole analysis assumes that the humans actually are correct, which is not really a perfect assumption, because I'm sure the analysts make mistakes. But to begin with, that's the best we have to train the AI with are the judgments of our human analysts. There is such a thing as an unsupervised model. A gadfly is unsupervised. A gadfly we trained on, hundreds of thousands of flights and many, many, many millions of pieces of data, and they were unlabeled. The model had to figure out what was normal and what was not normal without anybody telling it. That requires a really large amount of training data, and it requires certain characteristics that that the engine monitor data had, but Borescope image data really doesn't have. So this really needed to be trained with labeled images, meaning ones that a human analyst had tagged as being normal or abnormal. So that information would go into the training of the model. So how do you measure how well a model like this does? Well, there are two main performance metrics that are looked at, and they're called recall and precision. I don't think the best terms. Recall, another term for it is catch rate, is basically if you feed it a bunch of images, and some of the images in there are abnormal valves, what percentage of the abnormal valves did the model catch? So a high recall means that it didn't miss many burned valves. It caught most of the burned valves. The other metric, which is called precision or sometimes called correctness, it sort of looks at it the opposite direction. It says of all of the images that the model determined were abnormal, how many of them were really abnormal? In other words, how accurate were the assessments of the model? So, one kind of has to do with how many false negatives there were, and the other has to do with how many false positives there were. If precision is low, then you get a lot of false alarms about where the model says something's abnormal and it really isn't. If the catch rate is low, then you just miss a lot of things that you should have caught. So those are really the two performance metrics that we look at. And frequently, when you tune the model, it's a trade-off. You can increase the recall, but it'll decrease the precision, or vice versa. So you try to tune it to get sort of a happy medium where both of them are as high as you can get them. So again, recall says, did the AI catch most of the truly distressed valves? And precision says, when the AI said a valve was distressed, was it usually correct about that? So the way this stuff is analyzed is and AI has some really wonderful terminology, but what happens is you develop something called a confusion matrix. I don't know why they call it a confusion matrix, but that's what it's called. So this is a confusion matrix of the latest model as of yesterday, that was tested on that 10% test set, which wound up being 199 images that we ran through the model to see how well it did. And so if you add up the four numbers in the matrix, you should theoretically get 199. So if you look at this confusion matrix, the numbers on this diagonal are the ones where the AI model came up with the same conclusion as the human did. So there were 61 valves that the human thought was distressed, and the AI model also thought was distressed. There were 112 ones that the human thought were normal, and the AI model thought were normal. And the opposite diagonal are the ones where they disagreed. So you can see those were much smaller numbers, but there were 14 valves that the humans thought were normal that the AI model decided were distressed. And if you assume that the humans are always correct, then the AI model screwed up on those 14. And similarly, there were 12 where the human decided it was distressed and the AI model said it was normal. And those would normally be very early stage burn valves where it's a real subtle call that it's burned. So at any rate, when you crunch those numbers, you wind up with this information that these are the recall figures, and it basically said the AI caught 89% of the normal valves and called them normal, and caught 84% of the distressed valves and called them distressed. And of course, we'd like those percentages to be way up in the hopefully the high 90s, but at this point, I'm pretty impressed that this model is doing that well on such a limited training set. And if you look at the precision numbers, these have to do with when the AI makes a prediction, how often is it correct? And it says if the AI says a valve is normal, there's a 90% chance that it's right about that. And if it says the valve is distressed, there's an 84% chance that it's right about that. And again, the more training data we run into this thing, the higher those numbers presumably will be. So, sort of the bottom line is that at this very early stage, with very limited training data, the model is very good at detecting late stage burn valves. It's almost always right about those. It misses some subtle early stage valves, which isn't surprising because humans have problems with those too. They're pretty subtle. There's some tuning that we can do. One of the things we can do is because the model comes out with this confidence percentage, we can say, if the model isn't more than 90% confident, we'll disregard its conclusion or something like that. So that there's a lot of tuning that you can do, and it's always a trade-off that if it reduces false positives, it's going to increase false negatives or vice versa. So the tuning tries to get the thing in the sweetest spot that you can. So now the question is, at this very early stage, is this model, good enough to be useful? And the answer to that is kind of yes and no. It certainly is not at the point where we would use it as a replacement for human analysts and tell the human analysts they don't have to look at images anymore. Although, our goal is to get to that point, and I think we will. I personally think that the AI will ultimately wind up being better at this than humans are, but certainly not at this early stage of the game with such limited training data. It does a very good job of flagging images for human review that says you really ought to look at these because I think maybe something's wrong with them. And it's definitely going to help reduce our analyst workload right off the bat, but it's not going to put them out of a job. And because the false positive rate is not as low as we would like it to be, we don't think it's at the point where we can let clients see the predictions of the model. The predictions of the models will be going strictly to our analyst staff at the moment. We know from experience with previous AI things like the FIVA, the exhaust valve, the thing that predicts burned exhaust valves from looking at engine monitor data, that clients are very, very sensitive to false positives. If an AI says there's something wrong with their engine, and then it turns out that there isn't, they get very angry. So we need to have a very low false positive rate before we would make this client facing, and we're certainly not there yet. But I think we will be, and I'm frankly very encouraged that the model is doing as well as it is as early in the process as it is with such limited training data. So obviously, as our data set grows, and it's growing quite rapidly, the model performance will improve. We'll continue to retrain it on larger and larger label data sets. And our goal is to get it to be good enough that we can expose its predictions directly to clients and ultimately be in a position where they can upload images and instantly get a diagnosis, rather than having to wait 2 business days for a human to take a look at it. And I do think that this thing will get to the point where it's as good as humans at analyzing this stuff, and it's going to be a lot faster than humans at analyzing it for sure. And it'll free up our human analysts for doing more complicated things. Analysis of digital engine monitor data is a much more complicated task than looking at borescope images, because the engine monitor data is so multidimensional, and it's so we'd prefer to have our human analysts spending their time on the hard things, and leave the easier things to AI. So I'm pretty sure we'll get there, but it'll probably be another year or 2 before we get to that point. But I'm very encouraged at how this thing is going at this very early stage. And then we have all sorts of ideas for the future for doing correlations between borescope images and engine monitor data and stuff. But and that's a more complicated project. But first we have to get the Borescope AI to the point where we feel it's very, very trustworthy. So anyway, I think that the model is showing remarkable promise at this early time with such limited training data. It's pretty interesting that you can train an AI on a task like this, with only a couple of thousand images, because I would have guessed that it would take a lot more. The flagging capability is already useful. Full automation, meaning replacing the human analysts, is still ahead, but I'm sure we will get there. And we live in interesting times. We're embracing AI with open arms at Savvy, and just have all sorts of ideas of what we can do with AI. So basically, that's it, Tim. Just wanted to share this work in process with everybody, just because I thought it was kind of interesting. I'd be happy to take some questions, although I'm not an AI expert. So if the question is too deep, I'll have to take it as a homework assignment.
All right. Well, Jay was wondering, won't the image quality need to be high and consistent for this to work?
Well, as I mentioned, sometimes the quality of the images aren't good enough, and we just mark them as undetermined. The borescopes have been getting better and better, and the resolution of borescopes nowadays is full HD, and the pictures are very beautiful. But some people are still using older borescopes that have lower resolution and stuff. Consistency, is the reason we had to go to the 2-stage model, is because the images we get are very inconsistent. They're not framed the same way. The camera is not always in the same position. It's not always aimed at the same spot. We provide a checklist and a video and everything showing people how we want these images taken. And we give them, 11 specific images that we want them to take, including the exhaust valve head, which is what we've been focusing on here. But there's a lot of variation, obviously, between the different images we get. So that first submodel tries to get everything framed in a consistent way. The lighting isn't always consistent. The color rendering isn't always consistent, but it is what it is. And if humans can learn to accommodate all those variations, then AI can too. It just makes the job harder. It's just a more difficult thing to train. But pretty much anything humans can learn, AI can learn, given the right training data set.
Paul wonders, does your database record the specific borescope that produced the images? Could knowing this help with tweaking your AI model?
Actually, no, we don't know anything about what model borescope was being used. I'm not sure that would be very helpful. One thing that we noted that we aren't presently capturing, and we need to start capturing it, is, and this may be a little difficult because people don't keep very good track of this stuff, but we would really like to know how much time is on that exhaust valve. And because that would allow us to do some interesting analysis about what the lifespan of exhaust valves is, and how quickly. We do have a lot of interesting data now about Lycoming versus Continental valve issues, and the fact that Continentals burn valves a lot more than Lycomings do. Lycoming stick valves a lot more than Continentals do. And we always known that, but we've never been able to quantify it before. Now we're able to quantify it, but we're not capturing information on how old the valve is or how long it's been in service. Now, this is sort of a problem because people don't usually keep track of that. Everybody keeps track of time since last overhaul and stuff like that, but nobody really tracks time on individual cylinders. You can usually dig it out of the maintenance records, but sometimes it's not easy to do. You have to go back and see the last time the cylinder was removed from the engine for cylinder work and that sort of thing. But we would like to try to collect as much of that age data as we can. Not everybody will be able to give it to us. We're not going to make it a mandatory field because we understand that it's hard data to come by sometimes. But to the extent that we can get information about valves time in service, I think that would allow us to do some pretty interesting analysis of valve longevity. So, but no, we do not have information on what kind of borescope was used.
Gary wonders what borescopes are recommended.
Well, there are an awful lot of good borescopes available nowadays, and they're all pretty inexpensive. We mostly tend to use the Vividia VA400, which is a sub $300 borescope with full HD capability and a fully articulating tip. It's a rigid borescope with an articulating tip. A lot of borescopes are flexible scopes, and flexible scopes are very useful for a lot of things, but we don't particularly like flexible scopes when borescoping cylinders, because the flexibility of the scope makes it hard to get the camera positioned exactly where we want it. So we tend to like rigid scopes, or at least semi-rigid scopes. There are flexible borescopes that are fairly large in diameter and are fairly stiff, so that you bend it, you bend the probe, and it stays where you put it. And then there are the real flexible ones that kind of flop around, and they're good for getting into difficult small places, but they're not the best for cylinder inspection. But we tend to a lot of us use the Vividia VA400 because it's high quality and it's very inexpensive.
Donald was wondering, do you differentiate between engines running 100 low lead and unleaded auto gas?
We don't really have that information, although normally you can look at some Borescope images and tell immediately whether whether it's running unleaded fuel or not. You can tell whether it's been run lean to peak or not, just from the deposit formation. But that's not information that we solicit when people upload the data.
Linda wonders, do you think having more than one analyst rating the valve would improve the training model?
Oh, very likely. As I said, I'm the assumption in all these performance metrics is that the human analyst is what they call ground truth in the AI business. That's the and I'm not naive enough to believe that our analysts are sufficiently accurate in their analysis to be called ground truth. They're good, but they're human. And I'm sure that if we had 3 analysts look at the images and label them and see if they all agreed, we would have better training data, but it would require a tremendous amount of manpower because this is a lot of images coming in. So we've not done that. That would sort of be the tail wagging the dog. The analysts aren't really there to train the AI. They're there to serve our clients, and the AI is sort of a byproduct of their work, but it isn't their main goal.
Mark wonders, as the AI model improves to the point where we rely on it, how will we ensure that new human experts can be grown?
Well, I guess if we have good enough AI, we won't need any human experts, will we?
Is that where we're going?
I'm not sure. I don't think people are going to need to learn how to drive a car in the next generation. I don't drive my car; it drives me, and I trust it. I trust it more than I trust myself, frankly. So, not everybody is all in on AI. I'm kind of an all in on AI guy. I think it's great, and I think it's I've been alive for a long time. I'm 81 years old. I've been through the computer revolution. I was in on the ground floor of that. Been through the internet revolution and the smartphone revolution, but I think the AI revolution is going to have way more impact than any of those. It's really going to change pretty much everything that we do.
Roger wonders, can anyone upload images for analysis?
Sure. Anyone can upload images to the repository for free. If you want to have our analysts look at the data, then you have to get a Savvy Analysis subscription, which is not very expensive. All of the tools and stuff that we have, the repository and the report generator and all that stuff, we make available to anybody at no cost. All you have to do is create a free account on the Savvy platform and you're good to go. And that's also true of engine monitor data. But if you want our staff to analyze your data, then you have to have a Savvy Analysis subscription, but it's not very expensive. I think it's less than $200 a year.
Brad asks, do you record what cylinder associated with the image? Do you see certain cylinders with more burnt valves?
We do of course, record the cylinder. I don't think we've actually tried to do an analysis of whether cylinder position affects burning of valves. Obviously, we'd probably have to do that for by engine type, or at least by generic class of engine, 4-cylinder Lycoming, 6-cylinder Lycomings, 6-cylinder Continentals, that sort of thing. So we have the data to do that analysis. I don't think anybody's ever tried doing that, but would be quite easy for us to do. I recently was interested in finding out whether turbocharged engines burn valves more than normally aspirated engines, because you'd sort of think intuitively that they probably would. And so we ran an analysis. It took us 30 minutes or something, and came up with a whole bunch of data. And I made a bunch of PowerPoint slides from it. And it turns out that there's almost no difference. that turbocharged engines really don't burn significantly more valves than normally aspirated engines, which was a surprise to me. But it's nice to be able to do that sort of analysis. And we certainly could do an analysis by cylinder position, but I don't think we've ever undertaken that.
Scott asks, current naming convention includes date. Should it include tach hours on valve 2?
Well, it would be not. I don't think I'd put it in the file name, if that's what you mean. But it would be very nice to be able to enter that information. The problem is most people don't have that information because they don't track time and service for each individual cylinder, and they don't track time and service for cylinders since the last time the cylinder was off the engine. You have to dig back into maintenance data to get that information. Most people don't have it readily available, so I'm not sure a lot of people would be providing that data to us if we asked for it. But it would be really nice data to have. We're working on some projects digitizing maintenance logbooks using optical character recognition and AI. And if we, if we're successful in doing that, then we could probably automatically extract information on time and service for each cylinder from that data. But for humans to do it, it's a lot of work.
Matthew is wondering, will this tool help an A&P lessen his or her liability with regard to signing off on an engine as airworthy?
Oh, I don't know. That sounds like a lawyer question to me. I think mechanics obsess about liability way more than they should. If when aircraft have accidents, with about 80% probability it was the fault of the pilot, but the lawsuits are always against the aircraft manufacturer, the engine manufacturer, the propeller manufacturer, and pretty much anybody who had anything to do with touching the airplane. And, there's nothing you can do about that. The only thing you can do about that is carry insurance. And if you carry adequate insurance, then you shouldn't be stressing over it. You just try to do the right thing. And if you get sued, you turn it over to the insurance company. But mechanics are constantly obsessing about liability, and I think it causes them to make decisions that aren't probably the best decisions because they wind up not doing what's in their customer's best interest, but what's in their interest of lessening their perceived liability, which you really can't do. You just have to be insured.
Brian wonders, what false positive rate would you be comfortable with?
Just pulling a number out of the air. I think I would want the false positive rate to be less than 5%. I mean, I'd like it to be 0, but I know that's not going to happen. And I mean, it's probably not 0 for human analysts either, but we really don't want to make this stuff client facing unless we're pretty sure there are not going to be a bunch of false alarms, because we just know from experience that clients don't react well to that.
Paul wonders, do you have Rotax valve info in your database?
I'm sure we do. I don't have that information at the tip of my tongue, but I know we look at lots of Rotax engines.
Andrew wonders, is there correlations of one exhaust valve burnt to the other exhaust valve's health on the same engine?
We could do a statistical analysis of that. We've not done that, but I would, based on experience as opposed to data analysis, I would say there's no correlation whatsoever.
Walt wonders, how is training accomplished? Does a human label sample images and then the AI tool learns from that?
Yes, exactly. And, our analysts label the images as part of the work they're doing for our clients. And the tools that we've given them to do that, to do the analysis, were specifically designed so that the data would be captured in a form that could then be used as training data for an AI model. When they're doing the analysis and clicking on the buttons on their screen that says this is a heat distress valve in early stage or something like that, they're not thinking about that they're training AI. They're thinking about that they're preparing a report for the client. But as a byproduct of what they're doing, they're labeling training data for our AI projects.
Philip wonders, has it been hard to train your technical staff to detect the different stages of a valve going to the burnt stage?
I don't think so. It's something that that you do better with experience, and but no, I don't think it's hard to train. Humans are really good at pattern recognition, and it's hard to train machines to do that. Although nowadays it's getting easier and easier. But this assessing the condition of a valve by looking at the heat map of pattern of the exhaust deposits on the valve face or the valve head are that's a pretty easy thing to learn how to do. Healthy valves pretty much jump out at you as just having a symmetrical appearance, and any sort of asymmetry sort of catches your attention. And very early stage burning, you just tend to have a sort of a random asymmetry to it, and then as the burning progresses, you start getting formations that we call a smile. It's not a happy smile, but at any rate, it's sort of a semicircular area where the deposits are starting to get burned off because that area of the valve is running way too hot. But it's pretty easy to learn how to do that. You know, AOPA came out with a big wall poster years ago. I helped them put that together, showing lots and lots of valves, some healthy, some not so healthy, and to try to train mechanics how to tell the difference. Because in the early days, we were getting a lot of stuff that when borescopes first started getting used, there were a lot of mechanics that stick a borescope in a cylinder and say, "Oh my goodness, this valve is burned." And you'd say, "Well, how do you know it's burned?" And they say, "Oh, it's because it's red." Well, red, is a perfectly normal color for an exhaust valve. That's not how you tell whether a valve is burned. It really has more to do with symmetry and asymmetry than it does color. Valves in very late stage burning will tend, a hot spot will tend to turn green, but that can fool you because green can also appear on a normal valve, but it's a different kind of green. If the green that you see on a valve that's near failure is actually the metal itself turning green rather than the deposits turning green. So that to discriminate those two takes a little bit of training, but it's not a hard skill to learn.
Michael wonders, are the pics of the exhaust valves at each stage available for review on your website?
I don't really think so, no.
You said AOPA had a chart. Is that a good thing to try and look for?
Has a poster.
Uh-huh.
As I mentioned at the beginning, I'm working diligently on the development of a new training course for mechanics. It'll be available to anybody who wants to take it, and it's free, but we're really designing it as an IA renewal refresher course for IAs. IAs have to take about 8 hours of refresher training every year to keep their IAs intact. Well, there's several ways they can do it, but most IAs take 8 hours of refresher training. So we're developing an 8-hour refresher course that's just full of all of the latest technologies, the troubleshooting technologies, and engine monitor data analysis, and borescope inspections, and lapping valves, and all of that stuff. We figure if an IA, needs to take 8 hours of training, you might as well learn something new and valuable rather than just go through the same old stuff that he does every year. So, and an hour of that 8-hour course will be on borescope inspections and with a lot of detail on exactly how to do a good inspection and what to look for.
Well, that sounds
That'll
great.
be out. That'll be out at the end of October.
Roger wonders, can you have 2 or more AI quote unquote analysts trained, like training multiple human analysts, where they can review each other's conclusions?
Absolutely. In fact, I use many different AIs in my day-to-day work for doing research, and one of the AIs I use pretty regularly is Grok, which is Elon Musk's the XAI large language model, and Grok has a service that I think is called Super Grok or Deep Grok or something like that. That's it's $300 a month. It's kind of expensive, but it's a service where when you submit a prompt, it actually launches something like 10 different instances of the large language model to analyze your prompt and come up with an answer. and then the 10 answers go into a comparator to see if there's a consensus. So yeah, the exactly what you said is something that is being done today. Is having multiple AI models review something and then compare their results.
Well, Jerry says, amazing work, Mike. Keep it up. Thank you so much. Let's wrap it up here. Take a moment and share your closing thoughts with everybody. Looks like we had about 550 people logged in tonight.
Good. Well, you can probably tell that we're having a lot of fun with this stuff. I just love technology. I'm a technology freak, and this is the technology to end all technologies right now. Any rate, sort of the usual stuff. If you're not on my email list and would like to get on it for the monthly newsletter and other cool stuff like announcement of when this new training course is going to be available and stuff like that, you can put yourself on the list by texting the word SAVVY, SAVVY, to 33777, or you can stick around for the post-webinar survey and check a box on the survey. Tim would like you to do that. Or you can go to the savvyaviation.com website. There's a way to put yourself on the list up at the top of the homepage. My 4 books are still available on Amazon, Aircraft Spruce, EAA Bookstore. They're all available in audiobook form that you can get on Audible. Oh yeah, it's interesting. I do a twice a month podcast with 2 colleagues of mine, Paul New and Colleen Sterling, called Ask the A&Ps, which is basically a call-in podcast where aircraft owners and mechanics will call in with thorny maintenance issues, and then the 3 of us try to come up with solutions to them. You can get it wherever you get podcasts. It's widely disseminated, and if you would like to be on the show, you can send an email to podcasts@aopa.org, and our wonderful producer Ian Twombly will try to get you on the show. And I will mention, I don't have a slide on this yet because it's just in its formative stages, that I am about to start another podcast. It will probably be a couple months before it's first released, but it's going to be a monthly long form interview podcast where I just sit down and interview some, the most interesting aviation experts that I can find for a half an hour, an hour. And we made up a list of people that we want to interview that will keep us busy for the next 3 years. So when that's launched, I'll let everybody know. But that's in the pipe. I'm flunking retirement really badly, guys. At any rate, the next 3 webinars. The November webinar is called "Changing the Oil," and it's going to be a kind of a deep dive into why we have to change oil so often in piston aircraft engines, and what the right oil change interval is, because it's really not the same for every engine, and what kinds of things we're trying to get our oil to do and stuff. It's all about engine oil and stuff. December, I'm be doing a webinar called Quantifying Maintenance Risk, and it's basically a webinar about a brand new research paper that came out earlier this year. Very scholarly, very complicated paper, but basically two very skilled analysts took 17 years of NTSB accident data, GA accident, or data about GA accidents and serious incidents, the kind of thing that get into the NTSB database. And the question that the study sought to ask was, how much influence on GA accidents does maintenance have? And is there a relationship between the likelihood of an aircraft failure caused accident and the amount and the number of hours since it came out of annual? And the answer turned out to be very interesting, and they were able to quantify it and came up with some fascinating results that make it clear that the first 30 hours or so after the airplane comes out of annual has a very high elevated risk, and that that aircraft would actually be considerably safer if we didn't inspect them every year, if we inspected them every 2 years, for example. But there's a lot of really interesting quantitative data that came out of that study. I found it quite fascinating, and so that I'm going to present all that information, lots of tables and graphs and stuff that came out of that study in the December webinar. And we're actually looking at maybe enhancing that study by using some AI to increase the size of the set of accidents and incidents that are analyzed. But I'll get into that in the December webinar. And finally, is it really going to be 2026 already? The January webinar, which is January 7th, is entitled 9,000 Exhaust Valves. And I've touched on a couple of the things, but we've analyzed 9,000 exhaust valves and did a bunch of analysis of continental versus Lycoming and turbocharged versus normally aspirated and stuff like that. And again, I don't think anybody's ever collected that many images of exhaust valves before. So this is I think research that nobody's ever been able to do before. It's kind of interesting, but I'll be presenting a whole bunch of data about what we've learned in looking at all of these exhaust valves, not related to the AI stuff I talked about tonight, but just analysis that we've done on how often they burn and what kind of engines burn the most valves and that sort of thing. So that's what we're going to be doing in January. And that's all I got, Tim.
Fantastic presentation, Mike. Thank you so much, and best wishes going forward in continuing to develop this amazing new technology and applying it to our age-old airplane maintenance and inspection issues. What a deal it is. The old technology, old school, as old as it gets with airplane maintenance, and new school AI technology, combining the two. Good luck with that.
We're trying to drag it kicking and screaming into the 21st century, or at least into the 20th century. You know?
Well, congratulations, and thank you so much for sharing everything you're doing with us tonight. And to everybody who tuned in, thank you so much for joining us. Have a wonderful evening, everyone.
Yeah, thanks everybody. See you next month.